Good morning, everyone. So we're going to start our class today. So first of all, we've had pretty irregular classes due to this COVID situation. But hopefully, starting from this week, we're going to have more regular classes. Okay. All right, so let's see what happens. Okay, so our last class was actually over a week ago, and we talked about randomized algorithms. And we started talking about using randomization for hashing. Okay, so we saw that if you use normal hashing, which is not randomized, right, then you could have this behavior where you have lots of collisions so that all of your keys that you're trying to put into a hash table go into the same location, in which case all your operations are going to be very slow. Okay, so then we talked about this method using randomization to improve this situation. So we have this algorithm called universal hashing. Okay, and universal hashing can ensure that universal hashing. Sorry, where's my pen? Okay, here it is. Yeah, so universal hashing can ensure that if you have a hash table of size m, let's see, and then you put n keys into it, then all of the operations take order n divided by m time in expectation. Okay, and this is optimal because if you have n keys in m in a table of size m, then on average each table entry is going to have n divided by m keys inserted into it. Okay, so universal hashing is optimal in expectation. And the way universal hashing works is that we're not going to use a fixed hash function. Okay, instead we're going to use a big set of hash functions called capital H. And so now when you want to hash a set of keys, right? So if you're given a set of keys, then after that, you're going to pick a random hash function out of your family, capital H, of hash functions. And we're going to select this capital H in a way that if you pick a random hash function, okay, then for any two keys x and y, the probability that x and y collide is 1 divided by m, where m is the table size. Okay, so that basically means this hash function is behaving randomly, right? Because even if you just, so if you fix x and then you hash y to a random location, then you have a 1 over m collision probability. Okay, and here we're selecting a random hash function, and by doing this, we also achieve this, the same effect. Okay, so yeah, so we talked about, so if you have a universal hash family, okay, so we're going to see how to construct this, but if you have this universal hash family, then for any element x in your set, okay, the number of other elements y in the set which collide with x is expected to be n divided by m, okay? And the reason for that is simply that each y collides with x with probability 1 divided by m. And since there are n keys in total, then the expected number of collisions by linearity of expectations is going to be n divided by m. Okay, so that's one of our properties that we're going to use. And so next, we're going to see how to construct a universal hash family. Okay, so the construction is going to be in these 3 steps over here. So what we're going to do is, if you have so we're first of all going to fix the table size m. Okay, and then we assume that you know all the keys. Okay, so then after that, we're going to pick a prime number which is going to be bigger than all of your keys and all of your and the size of your hash function. Okay, so you need to pick a very large prime number to start out with. And I'll show you later how we can actually achieve this, how it's possible to select a very large prime number in a very efficient way. Okay, but for now, let's just assume that you can pick such a large prime number. Okay, then what we're going to do is we're going to define this function h sub ab of k, where a and b are 2 numbers. Okay, and the function is simply defined as, so k here is a key, and the function is just going to take the key times a plus b, and then take it modulo this large prime value. And then you're going to take another mod. Okay, and then you're going to the second mod is modulo the table size. So then after you do all of these steps, you're going to get a value between 0 to m minus 1. And so that's going to be a location in your hash table, right? Because your hash table has size m. Okay, so that's just one of these HAB functions. And in total, we're going to define this universal hash family, capital H sub Pm, right, where P is a prime number and M is your table size. And this family is going to consist of all possible HAB functions, basically, right? So then what we're going to do is to pick A in this range from 1 to P minus 1. And then we're going to pick B in the range from 0 to P minus 1. Okay. So in total, there are P minus 1 values for A, and there are P values for B. So in total, there are P times P minus 1 possible values for HAB. Okay, so we have P times P minus 1 different hash functions in this universal hash family, HPM. Okay, does that make sense? Any questions about this? Okay, so we have this large set of hash functions. And then, again, the way to use this is that we're just going to pick a random function out of this large HPM set. Okay. All right, so now what we need to do is we're going to prove that HPM is a universal hash family. Okay. So by the way, I'm giving one particular construction for a universal hash family. Okay. There are different ways to construct other universal hash families. So I'm just giving one which is pretty easy to construct, and it's often used in practice. Okay. All right. So then let's prove that HPM is universal. So what we're going to do is we're going to pick two different keys x and y. Okay. And we want to see what their collision probability is. Okay. So first of all, we know that x and y are both less than p, right? Because we pick the prime to be larger than all possible keys. All right. So now, suppose you picked a random hash function HAB, okay? Then what that's going to do is, if you have these two keys x and y, then HAB is going to compute this function over here. Okay? Now, there are two mods in this function. So let's first ignore the outer mod, okay? Let's just focus on the inner part over here. Okay, so if you just focus on the inner part, then let's define R to be AX plus B modulo P. And let's define S to be A times Y plus B modulo P, right? So X and Y are the two different keys. Okay, now, first of all, we're going to show that R is not equal to S, okay? And the reason is that if R is equal to, let's do R minus S, okay? Well, R minus S is congruent to A times X minus Y modulo P, right? Because the B's just cancel out when you do R minus S. Okay. And this value here is going to be non-zero, okay? Because A is less than P, right? And X minus Y is also less than P. And because P is a prime number, then the product of A and X minus Y is not going to divide P. Okay, so therefore A times X minus Y modulo P is non-zero. Okay, all right, so that's one fact, that we have R is not equal to S. Okay. Now, the next fact that we're going to have is that, so we're going to select, so in total, we have a bunch of possible choices for A and B, right? We have P minus 1 choices for A and P choices for B. And now what we want to claim is that for each of these choices of A and B, we're going to produce a different pair RS. Okay, so once you fix X and Y, then for each different A and B that you choose, you're going to produce a different pair R comma S. Okay, and why is this true? Well, it's true just because, here, let me try to erase some stuff over here. So just to clean things up. All right, so what we have is, so we have this expression over here, right? And now if you take this expression, then we can use it to solve for A. Okay, because what you need to do is, so we're saying that R minus S is congruent to A times X minus Y modulo P. Okay, so then what you can do is basically divide out, you can basically divide by X minus Y on both sides. Okay, yeah, so we can divide out the X minus Y over here, and then on the other side, you need to multiply by, we're not really going to divide by X minus Y, okay, because we're working modulo P. So we're not working in the reals, we're working modulo P. But if you're working modulo a prime number, what you can do is you can define the multiplicative inverse of X minus Y, okay, with respect to P. And then you can multiply by that value. Okay, so when we do that, you're going to get that A is equal to this, this expression over here. Oops, what happened to it? All right, yeah, we're going to get this expression over here, okay? All right, and then once you have A, then you can also use that to solve for B, okay? Because once you have A, right, if you know the value of A, then, you know, we know R, of course, right? Then you can, then B is simply equal to R minus AX, okay, modulo P. So then once you know A, you also know B. Okay, so the point of this is to say that if I give you a pair RS, okay, then you can uniquely produce another pair AB. Okay, by solving for A and B using these two expressions. And this means that each different A and B is going to lead to a different pair R and S. Okay. Sorry, yeah, okay, so this is the second fact that we have over here. And now we know that in total we have P times P minus 1 pairs, different pairs A and B, right? And since each of these AB pairs is going to lead to a different RS, right? Then we're going to have P times P minus 1 pairs RS. Okay, and also we know that R does not equal S by our previous claim. Okay. And so, so this means that if you pick a random AB, then because each AB maps to a unique RS pair, then if you pick a random AB, then this is going to produce a random RS pair. Okay, so that's one of the key points, right? So the way that we use the universal hash family is we pick a random HAB function, okay, and we do that by picking a random B pair. And this is going to produce a random RS pair, right? Where R and S are defined as over here. Okay. All right. So now we're gonna. So previously we only looked at. I'm sorry, this is so slow, my computer. So previously we only looked at this part of the HAB function, right? We didn't consider the modulo M part yet. Okay, so now we're going to add back the modulo M part. Okay, so now what we have is that, remember, we're trying to figure out the probability that X and Y collide. Okay, and so X and Y are only going to collide if R is congruent to S modulo M. Okay, right, and now suppose you fix R. Okay, then if you look at how many other S's, S not equal to R, are congruent to R modulo M. Well, S has P possible values from 0 to P minus 1. Okay, and since we know that S is not equal to R, then there are P minus 1 possible values for S. Okay, and then yeah, and then so the number of values which are congruent to number of R, or a number of S which are congruent to R modulo M, it's just going to be P minus 1 divided by M. Okay, and now we know that when you select a random AB, you're going to get a random RS out. Okay, and so that means that if you fix the R, if you like condition on an R, okay, then the S that you get out is going to be random with respect to R. Okay, and so that means that if you pick a random S, okay, then what is the probability that R and S are actually congruent modulo M? Well, there are only P minus 1 divided by M S values which are congruent to R. Okay, and then if you pick a random R value, well, random S, which is different from R, well, then you have P minus 1 choices for S. Okay, and only P minus 1 divided by M of them actually are congruent modulo M. Okay, so that means that if you pick a random S value, your probability that R and S are congruent is going to be 1 divided by M. Okay, it's the number of values which are congruent to R, right, divided by the number of possible values for S. Okay, and this is going to be 1 divided by M. Okay, and so this shows, and you know, if X and Y collide, okay, then that means that R and S are congruent to each other. Okay, and we just showed that this happens with a probability 1 divided by M. So therefore, we've shown that for any two keys X and Y, if you pick a random HAB function, right, then x and y are going to collide with probability 1 divided by m. And so this means that this capital HPM family, right, this is a universal hash family. Okay, are there any questions about this? Okay, yeah, so this is one possible construction for a universal hash family. Okay, and yeah, and once you have this, then you have this property that in expectation, any two keys, or sorry, any operation is going to take expected time n divided by m. Okay, so so now we're going to move on to a different topic. Okay, so we're done with universal hashing, and now we're going to talk about a final hashing topic, which is called perfect hashing. Okay, so the idea for perfect hashing is that, so previously we've seen that if you use just normal hashing, then you can get order n worst case behavior, right? And if you use universal hashing, you're going to get order n divided by m expected behavior. But even though you're getting expected n divided by m time, it's possible even with universal hashing that you get order n worst case behavior, right? Because sometimes you can pick a bad hash function. When you pick a random hash function, right, most hash functions are good, but there are some bad hash functions also. And so if you're unlucky and you get one of these bad hash functions, then you can actually get order n worst time behavior, even for universal hashing. Okay, so the final thing we're going to look at is something called perfect hashing. And perfect hashing is going to ensure that you never have any collisions. Okay, it's going to guarantee that you never have any collisions in your hash table. And so that's why it's called perfect hashing. Okay. However, for perfect hashing, there's a restriction, which is that you have to work with a fixed set of keys. Okay. So this means that you cannot like add more keys to your set. Okay. So what you have to do is you just have to fix your set of keys, and you can only maintain a static set. Okay. And so for the static set, you cannot do any insert operations. You can do delete operations, and you can do find operations. And all of these are guaranteed to work in constant time because there's no collisions, right? It's guaranteed that you don't have any collisions. But you cannot insert additional keys. Okay, so where this might be useful, so you know, this is you know, a big restriction that you can't add more keys. Okay, but this can still be useful in some cases. So for example, you know, we have certain types of media which are not rewritable, right? You cannot write more things onto them. Okay, so for example, if you get a Blu-ray disc, right, then you cannot write more data onto the Blu-ray disc once you've written it. Okay, I mean, there are rewritable Blu-ray discs also, but you know, if you just go for the standard ones, then you know, you can only write them once. All right, so that's one situation where you might need to maintain a fixed set of keys, but you want very fast operations. And this is one situation where you might use perfect hashing. Okay, so let's see how perfect hashing works. Okay, so suppose you're trying to store n items, and you want to guarantee that you don't have any collisions. Then perfect hashing is going to make use of universal hashing. Okay, in fact, it's going to use two levels of universal hashing. So what I mean by that is that we're going to make a data structure which looks like this picture. Okay, so then we have a top level hash table. Okay, so we have this capital T, which is your top level hash table. And the size of the hash table, right, the size m is equal to the number of items that you're trying to store. Okay, so in this example, I guess they're trying to store 9 items. Okay, so then you have a hash table of size 9. And then what you're going to do is associated with the top level hash table, you're going to have a top level universal hashing family. Okay, right. And then from that top level universal hash family, you're going to pick a function h, and you're going to use that to hash your keys to different locations in this top level table. Now, when you do that, you could actually get some collisions. Okay, so for example, in this case, we have 3 different keys, right? 60, 72, and 75, which all hash to this location using the top level h function. Okay, And then next, what we're going to do is associated with this location over here, we're going to put another hash table. Okay, so this is going to be the second level hash table. And within the second level hash table, again, we're going to use universal hashing. Okay, and so for each of these, each table location S sub j, okay, where j is like from 0 to the m-1, the size of the table. We have a different hash function h sub j. Okay, so yeah, so this location has one. Oops, why can't I write here? Okay, so this has a hash function, and this has a different hash function, and this place has a different hash function. Okay, so every location in this table is going to have a different hash function, second level hash function. And these second level hash functions are going to ensure that you do not have any collisions. Okay, so for example, in this second level hash table, right, you see that we're putting 3 items in here and we don't have any collisions. Okay, likewise over here, right, we put 4 items into this location and we don't have any collisions. Okay, yeah, so that's the basic idea for how this works. So let me give you some more details. So now suppose using the let me erase some of this stuff. Okay, so we have this h function, which is the top level hash function, right? That is going to produce a location in this top level hash function hash table t. And then for each location in t, you have a different second level hash function h sub j. Okay, now how do you define this h sub j? So what you're going to do is you're going to look at how many keys actually hash to location j. Okay, so for example, for this location, you have 3 different keys that hash over here. Okay, and then you're going to set the size of this hash table at location 3 to be the square of the number of keys which hashed to that location. Okay, so here you're going to set the table size to be 9. Okay, and over here you have 4 different values which hash to this location in capital T, and so you're going to set the second level hash table to be size 16. Okay, all right. So then once you fix the size of all of these hash tables, so this thing has size m always, right? And these tables have size. So this has size n2 squared, and this has size n7 squared. Okay. Right. So then we're gonna so once we know the sizes of all of these hash tables, the top level and all of these second level hash tables, right? Then we can define universal hash families for these table sizes. Okay. So for example, in this example that I'm showing, the way that we define these hash functions is like this. Okay. The top level hash function is going to be is this function, which is chosen from some universal hash family. Okay. And then all of the other second level hash functions are also of this form, right? However, here the table size is going to be m sub j, okay, where m sub j is equal to n sub j squared. All right, are there any questions about how this perfect hashing works, how the algorithm works? Okay, so to hash a key, right, all you do is you first apply the h function, right? That takes you to a location in capital T, and then you apply whichever, if you get to location j, right, then you're going to apply the hj function, and that's going to put the key into some location in a second level hash table. Okay, so that's the algorithm. Okay, so then what we're going to show is that we can ensure that in these second level hash tables, there are no collisions at all. Okay, and so that means that all of the operations are going to take worst case constant time. Okay, because if there are no collisions in the second level hash table, then to hash a key, you just apply the top level hash function, that's constant time, right? And then you apply the second level hash function, which is again constant time. And since you don't have any collisions, you don't have to search through any lists. Okay, so altogether you have constant time operations for find and delete. Okay, so now the main thing that we have to think about is how much space is this going to take? Okay, because now we're not just keeping one hash table, right? You're not just keeping this capital T thing over here, right? Yeah, you're not just keeping capital T. You're going to keep capital T plus all of these little hash tables. And so we want to make sure that these second level hash tables do not take too much space. Because if altogether you take a huge amount of space, right, then it's easy to ensure that you don't have any collisions, right? If I try to insert 10 keys and I use a hash table of size 1,000,000, right, then it's very easy to ensure that there are no collisions. Okay, so we have to make sure that our total space usage is not too large. Yeah, so I see there's a question, but let me just finish my what I'm saying over here. So what we're going to show is that altogether, okay, this entire hash table, the top level plus all the second level hash tables. Okay, so the size of that is going to be, well, this is for the top level hash table, right? And this is the size of all the second level hash tables. So we're going to show that this total size, okay, is going to be order m. Okay, where m is, order n. Okay, what I want to do is, I want to show that this is order n, where n is the number of keys that you're storing. Okay, so even though we're using a lot of different hash tables, the total size that we're using is simply proportional to the number of keys that we have. And this is optimal, of course, right? Because if you want to store n keys, you have to use order n storage, unless you use some sort of compression or something, okay, which we don't think about. Okay, so therefore, perfect hashing and normal hashing are going to use the same amount of space, okay? And perfect hashing doesn't have any collisions. Okay, so let me just take a look at this question. Why are some locations? Okay, yeah. So these locations indicate that we don't have any keys which hash to this top level location. Okay, so for example, here you have 3 keys, 60, 72, and 75, which hash to this T2 location, right? And then, these entries indicate that there's nothing. So when you hash 60, 70, 72, and 75 into this table S2, right, they're going to get placed into these 3 positions, and all the other positions are empty. Okay, and likewise, in the top level hash table, this slash indicates that there are no keys which hash to this top level hash location. Okay, any other questions about how this algorithm works before we start the proof? Okay, so all right, so then let's try to prove this fact, okay, which is that in total we're going to use linear storage. Okay, so we need a lemma first, which is that okay, so the lemma is saying that if you store n keys. Okay, so here n is like anything. Okay, so n. So in this lemma, n is not the n from the previous page. Okay, but just if you try to store any n keys, and then if you use a table, a hash table of size n squared, okay, and if you use something like universal hashing, then you have at least a 1/2 probability that there are no collisions in your hash table. Okay. But notice here that in order to store n keys, you have to use a very large hash table, right, of size n squared. Okay. But if you use such a large hash table, then you have a very good probability that you don't have any collisions. Okay, so the proof of this is that, well, first of all, if you have n keys, then if you look at all pairs of keys which can collide, there are only n choose 2 pairs of keys which can collide. And because you're going to use universal hashing, then each collision, so any pair of keys are going to collide with probability 1 divided by m, where m is your table size, right? And since here you set m to be n squared, then each collision occurs with probability 1 divided by n squared. Okay, so therefore the expected number of collisions is just your total number of pairs of keys which can collide times the probability that each of them does collide. Okay, so it's going to be this expression over here, which is going to be less than 1/2. Okay, so therefore your expected number of collisions is less than 1/2. Okay, and so now you can apply this thing called Markov's inequality, which says that the probability. So because your expected number of collisions is less than 1/2, then by Markov's inequality, the probability that you get more than one collision, okay, is going to be less than or equal to the expected number of collisions divided by this value 1. Okay, and the expected number of collisions is less than 1/2. So therefore, the probability that you get at least one collision is no more than 1/2. Okay. Right. So then this means that why do we need this lemma? Okay. What we want the reason we want this lemma is because remember that the way that we build these let me erase some of this stuff over here. Okay. The way that you build these second level hash functions is that you're going to set the size of the second level hash function to be this over here. You're going to set the size of each second level hash function to be the square of the number of keys which go to that location, right? Like over here, right? We have 3 values which go to this location. So you're going to set the hash table size to be 9. Okay. And so because of this lemma, which says that if you use a table of size n squared to store n values, then you have a 1/2 probability that there's no collision. Okay. Then that means that whenever you build each of these second level hash functions, there's a less than 1/2 probability that you have any collisions in this hash table. Okay. But there's still some probability that you have a collision. And we want to avoid any collisions, right? We want to guarantee that there are never any collisions. Okay. So then what you can do is you can try to build the second level hash function. Okay. And if you happen to get a collision, right, because there is some probability you get a collision, right? But if you get a collision, then just pick another random hash function and just rebuild your hash table. Okay, and so each time you do this, you have at least a 1/2 probability that you don't have any collisions. Okay, so in expectation, you just need to rebuild your hash table 2 times before you get a hash table with no collisions at all. Okay, so this is how you can ensure that each of these second level hash functions, hash tables, does not have any collisions. Okay, you just keep rebuilding until you don't have any collisions. And on average, you only have to do this twice. Okay, so right. So the final part of this is so now we can look at the expected we can look at the size of the hash table. Well, yeah, the expected size of the hash table. Okay, of the entire hash table. Okay, so what we're going to do is we're going to prove this fact. Okay, we're going to prove that if you add up all of these second level hash tables, okay, then their total size is going to be in expectation no more than 2 times n. Okay. All right. So the way that we're going to do this is we're just going to take the sum, and then the first thing is to rewrite the sum, is to just expand the sum this way. Okay. So you can just check the algebra that this expression over here is equal to nj squared. All right. So now we've so now by linearity of expectations, you can break this sum into 2 parts. Okay, into this first part and the second part. All right, so we're going to look at the second part first. Okay. Now, if you look at the second part, right, so we're summing up nj choose 2 for all the different j's. Okay. So what is this? Okay. So if you sum up nj choose 2, then this is actually equal to the total number of pairs of hash keys which collide. Okay. So right, because what happens is in the first level hash table, for each location j, you have nj keys which hash to that location j. Okay. And then if you look at those nj keys, then all pairs of them collide. So that's going to produce nj choose 2 pairs of keys which collide. Okay, at location j. Okay. But then if you look at any pair of keys which collide, then they have to collide at some location j. Right? So therefore, if you add up all of these values for all of the possible j's, right, then that's going to account for all pairs of collisions between pairs of keys. Okay, so this sum actually includes all pairs of collisions for your entire top-level hash table. Okay. All right, now how many collisions should there be in the top-level hash table? Well, because you're using universal hashing, okay, and you're inserting n keys, right? Then there are n choose 2 pairs of keys. And each one of them has a 1/n probability of colliding in the first level hash table. And so therefore, the expected number of collisions in the top level hash table is going to be n minus 1 divided by 2. Okay. And so that means that this sum over here, right? Sorry. Okay. This sum is exactly equal to the total number of pairs of keys which collide in the top level. Okay, and so this is going to be equal to n minus 1 divided by 2. Okay, all right. And then next, we're going to do the first part of this sum. And this is easy because here you're just summing up over all the nj values. Okay, and so so that's just equal to n, right? Because you're inserting n keys, and if you look at the number of collisions at any of the locations and you add up all the collisions, that's just equal to your total number of keys. Or sorry, not number of collisions. If you add up the number of keys which hash to a location in the top level, okay, so the top level collisions, okay, then that's just equal to the total number of keys that you inserted. Okay. Okay, so then, so therefore what we have is that we can go back to this expression over here, and we have that this part over here is less than or equal to n, right? And then this part, the expected part, is going to be no more than n minus 1 times divided by 2. And then if you multiply by the 2 over here, right, then you get that altogether, this sum is going to be at most 2 times n. Okay, so this means that the secondary hash tables, right, the total space that they use is expected to be less than 2n. Right, and then if you add this together with the top level hash table, which also uses size, which also has size n, right, then you see that this entire hash table, the top level plus the second level, right, they have total size 3n in expectation. Okay, so so are there any questions about this analysis? All right, so then that's all I'm going to say for perfect hashing, and all right, so then we're going to move on to the next topic for today, if there are no questions. Okay, so then let's move on to the next. Let's move on to today's lecture, which is over here. Oops. Sorry. Let me try to open this. Okay. All right. Okay. So then today we're going to keep talking about. So for the next lecture, we're going to keep talking about randomized algorithms, and we're going to look at a data structure called Bloom filters. Okay. So this is a very widely used data structure, and it's based on randomization. And then if we have time, we're also going to look at some string matching algorithms. Okay, if we don't have time, then we're going to push this string matching to the next lecture. Okay, so first of all, let's look at Bloom filters. Okay, so a Bloom filter is a data structure. Okay, so we just looked at hashing, which is a data structure. And a Bloom filter is also a data structure, and it does something similar to hashing. So Bloom filter can also implement a set, okay? Meaning that you can insert things into a set, you can delete things out, or sorry, you can insert things into the set, and you can check whether certain things are in the set, okay? However, a Bloom filter is sort of a weaker data structure than a hash function because the Bloom filter does not support delete operations, okay? You can only insert things into the Bloom filter. You cannot take things out of the Bloom filter. So later on in this lecture, we're going to look at some variations of Bloom filters where you can support some kind of limited delete operation. Okay, it's not some sort of arbitrary delete operation, but you can do some kind of deletes. Okay, but the basic Bloom filter only supports insert operations and find operations. Okay, and furthermore, you can only keep track of which keys are in the Bloom filter. Okay, or you can only keep track of keys which are in the Bloom filter. The Bloom filter cannot keep track of any values associated with the keys. Okay, whereas a hash table, right, you can store both a key and a value for that key. Okay, yeah, so the Bloom filter is kind of like a hash table, but it's actually weaker than a hash table because of all these limitations. Okay, so then why would we care about Bloom filters, right? If it's weaker than a hash table, why not just use a hash table? Okay. But the reason that Bloom filters are very widely used is because they use very little memory. Okay, they can use much less memory than hash tables. So for example, if you look at a Bloom filter, then when you store a set of items, then on average, you can use something like 10 bits per item that you store. Okay, 10 bits per item. Whereas if you look at a hash table, right, then oftentimes you're going to use a lot more memory than 10 bits. Right. So for example, if you're storing, let's say, if you're storing integers, Okay, so even just to store the key, if you have integers, you need 32 bits. Okay, and then if you have pointers between those integers, that's another 32 or 64 bits, right? And then if you're not storing integers, if you're storing something like strings, right, then that's going to be even more bits. Okay, so if you try to store things using a hash table, you might use tens or even hundreds of bits per item. Whereas for a Bloom filter, right, you can usually get away with using something like 10 to 15 bits. Okay. So we'll talk later about exactly how much storage Bloom filters use, okay, because that's actually a tunable parameter. Okay, but we'll look at how to tune that parameter later. But the point is that Bloom filters in general are going to use a lot less memory than hash tables. And so, so this is why they're popular, okay, because they can save a lot of memory. Right, but Bloom filters have another problem. Okay, so we already said that they do not support delete operations and they don't keep track of values, right? So that's already two problems. But they have yet another problem, which is that these Bloom filters are approximate. Okay, meaning that so we're trying to keep track of a set, right? But the Bloom filter can actually have false positives, meaning that if you ask the Bloom filter whether some element is in the set, and suppose the Bloom filter says it is in the set, okay, then sometimes that answer is actually incorrect, meaning the item is actually not in the set, but the Bloom filter says it is in the set. Okay, so you can get a false positive. Okay. Now, on the other hand, but you can bound the probability that you get a false positive. Okay, so we can show that by using more storage, you can greatly reduce the false positive probability. Okay, so for example, if you use basically 10 bits per item, right, then you can ensure that you get a 1% false positive probability. Okay, if you use something like 15 bits per item, you can get a 1 in 1,000 false positive probability. Okay, so you could get false positives, but we can always decrease that probability by using more memory. Now, one good thing about Bloom filters is that you never get false negatives. Okay, meaning that if the Bloom filter says an item is not in the set, then it's guaranteed to be not in the set. Okay, if it says that it's in the set, it could be a false positive. But if it says it's not in the set, it's definitely not in the set. Okay, all right, so then, so before we talk about how Bloom filters, how to implement Bloom filters, let's first look at some applications for Bloom filters. Okay, so one application is, suppose you've got a big database. Okay, so so now you want to check whether certain items are in the database, and to access the database, it's actually quite expensive, right? Because we know that databases are very complicated. So to make any query to the database, it's going to take you a long time. Okay, so now we can use Bloom filters to try to speed up this process of checking whether some item is in the database. So what we do is we just create a Bloom filter to keep track of all of the items which are in the database. Right? So the Bloom filter implements a set so it can keep track of which items are in a set. Okay? Right, so now if you want to check whether something is in the database, then first of all, you're going to check whether it's in the Bloom filter. Okay? And if the Bloom filter says your item is not in the database, okay, then we're guaranteed that the item is not in the database either, because a Bloom filter doesn't have any false positives. False negatives. Okay, yeah. So if we check the Bloom, and it's very quick to check a Bloom filter. Okay, so we're going to quickly check the Bloom filter, and if it says that an item is not in the database, then we're not going to do that expensive query to the database. Now, on the other hand, if the Bloom filter says the item is in the database, right, then we're going to go query the database for the item. Okay, and oftentimes the item will actually be in the database. Right? Because if the Bloom filter says something is in the database, then usually it actually is in the database. However, there is some small false positive probability, meaning that the filter says the item is in the database, but the item is actually not in the database. Okay? So there's a small probability that you make a useless query to the database. Okay? But usually when you query the database, it's actually in the database. Okay, so then altogether, what we did was by first of all using the Bloom filter before you actually query the database, then on average you can save a lot of time. Okay, because if the item is not in the database, right, then you don't bother making this expensive query. And if it's in the database, right, then you know, when you ask the Bloom filter, when you ask the Bloom filter, usually when you get a yes answer, it actually is in the database, and there's a small probability that you get a false positive, in which case you wasted time. Okay, but that probability is very small. Okay, so that's one basic application for Bloom filters. And yeah, so this is another application, but it's kind of similar to this. Okay, so so what I'm going to do, so I'm not going to go through this too much. You can read it on your own, but it's basically, you know, if you're doing some sort of peer-to-peer like file sharing network or something, okay, you can basically use the same idea where instead of querying another node in the network, which is quite expensive, right, you can use a Bloom filter to keep track of which nodes have which items. And you can start by querying the Bloom filter. Okay, so that's a very cheap operation, and that allows you to oftentimes not have to make these more expensive operations to the nodes in the network. Okay, yeah. So basically, Bloom filters, right, as the name implies, they're used as a filter operation to some more expensive operation. Okay, all right, so now let's see how Bloom filters work. Okay, right, so the Bloom filter is actually a very simple data structure. So what you do is you just construct an array of size m. Okay, so you get to pick how large you want to make your Bloom filter of size m, and then you make an array of that size, and this is actually a bit array. Okay, so all the values are either 0 or 1, and initially they're all zeros. Okay, so the next step is that we need to choose k independent hash functions. Okay, and the hash functions each, they're all going to map keys. So we're trying to insert a bunch of keys into the Bloom filter, right? So the hash functions are going to map the keys to one of these array locations. Okay, so it's going to produce a value from 1 to m for each possible key. Okay, and you're going to choose k of these hash functions, and then you get to choose how large you want to make k. Okay, so we'll talk later about how large to make k. Right? Yeah, but we have these hash functions, and we're going to assume that these hash functions are independent from each other. Okay, so so if you take the first hash function and the second one, and then if you fix a key, right, then basically there's no correlation between where the key hashes using the first function versus any of the other hash functions, okay, or any pair of hash functions. Okay, so then and that's all we need for this Bloom filter. Okay, it's just this bit array and k hash functions. Okay, so now if you want to store a key x, okay, then what you do is you just apply all your hash functions to x. Okay, so each of these hash functions is going to produce an array location. Okay, and then you're simply going to set that array location to be 1. Right, so each array location is either 0 or 1. And initially, they're all zeros. And so when you want to store this key, you're going to find a bunch of these array locations, and you just set all of them to 1. Okay, yeah, so for example, if you want to store this key x1 here, right, and suppose it hashes to these 3 locations, you just set them to be 1s. Okay. And then later, if you want to store another key x2, right, that could also hash to a bunch of locations, and you also set those locations to 1s. And notice that x1 and x2, right, they both hash, so they actually have a collision in one of their hashes. Okay, and that's not a problem, right? So all you do is you just keep this value here to be 1. Okay, if both x1 and x2 hash to the same location, you just set that location to be 1. Okay. All right, and so the next thing is that you need to be able to check whether a key is in the set. And to do this, right, so if you want to check whether key x is in the set, then again, you're going to take all your hash functions and apply to x, and that's going to produce k locations. Okay? And then you're simply going to go read all those locations. And if all those locations are 1, okay, if all the values are 1, then you're going to say that x is in the set. Okay? But if any of the locations are not 1, okay, if there are any zeros in these k different locations, then you're going to say that x is not in the set. Okay, so for example, if you want to check for x1, right, then you're going to hash x1 to this location, this one, and that, and this one, right, and then you see that they're all ones. So therefore, you say that x1 is in the set. Okay, if you want to check for some other x, which maybe hashes to, let's say, these locations, right, well, then one of these locations is actually 0. So then you're going to say that this x is not in the set. Okay. Right, so that is the way that Bloom filters work. Okay. All right. So now we're going to look at we're going to prove the correctness of the Bloom filter. Okay. So basically, we have to ensure that this this search function or this checking function over here, we have to make sure that this works correctly. Okay. So there are two parts to ensuring that it works correctly. One is that if the search function returns no, okay, so if the search function says that x is not in the set, okay, then we want to make sure that we do not have a false negative. So we want to make sure that x is actually x is definitely not in the set if the search function says it's not in the set. Okay, and this is true because if the search function says x is not in the set, okay, then this means that at least one of these locations that it checked was equal to 0, right? Because if all the locations are 1, then the search function is going to say x is in the set. Okay, so at least one of those locations was a 0. Okay, but then that means that x cannot actually be in the set. Because if x was in the set, right, then when you inserted x into the set, you would have set all of these locations to 1s, right? But we know that one of these locations is actually 0. And so that means that x was never inserted into the set. Okay, so that means that we never get false negatives, right? If the Bloom filter says something is not in there, it's definitely not in there. Okay, now what about what if the Bloom filter says something is in the set? Okay, so that's going to happen when all of these k locations that you check are equal to 1. Okay, so in that case, so one possibility is that x was actually inserted into the set. And when you inserted x, right, you set all these k locations to be 1. Okay, so if the Bloom filter says x is in the set, then it's possible that x was inserted into the set. Okay. However, there's also another possibility, which is that you get we got a false positive. Okay, so to see how that can happen, suppose you have a Bloom filter where you inserted x1 and x2. Okay, so there are only 2 items in the set. And now, suppose you check for a third item, x3, which is not in the set. Okay, but suppose it just so happens that x3 hashes to these locations, and these locations were all set to 1 by x1 and x2. Right? So you never inserted x3. But when you go check for all these 3 locations, you see that they're all 1s. So in that case, the Bloom filter is going to say that x3 is in the set. Okay, and that's a false positive because x3 is actually not in the set. Okay, so this is how you can get a false positive. Okay. But what we're going to show is that the probability that you get a false positive is actually small. Okay, so the next thing to do is to bound the probability that we get a false positive. Okay, so to do this, we need a few parameters. Okay, so the first parameter is going to be k, which is the number of hash functions that we have. Okay, second parameter is m, which is the size of the hash table. And the third one is n, the number of keys that you insert. All right, now we're going to assume that these hash functions basically behave randomly. Okay, so the hash functions themselves are deterministic functions. Okay, so we said last time with hashing that we have to always use deterministic hash functions. Okay, but we're going to assume that their behavior is kind of random in the sense that if you give the function, if you give the hash function a key, it's going to map the key to basically a random location. Okay, so in practice, we said that there are hash functions which achieve this kind of behavior, right? Yeah, so we'll just assume that this happens. So that means that when you insert a key, then because you have k different hash functions, right, and each of them is random, then you're basically setting k random locations to 1s. All right, now let's fix any particular position I in the table. Okay, Now the probability that I is set to 1 by a single hash function is going to be 1 divided by m. Right? Because a hash function just takes a key and sets a random location to 1. Okay, so the probability that it sets location I to 1 is 1 divided by m. And so the probability that so initially I was 0, right? So the probability that I stays 0 is going to be 1 minus 1 divided by m. Okay, but we're not just using one hash function, we're actually using k different hash functions. So therefore, after k hashes, the probability that I is still 0 is going to be this probability to the kth power. Okay. And now this is just for one item, right? For one item, you do k hashes. But if you insert n items, then you're going to do n times k hashes, right? So the probability that I stays 0 after all n times k hashes is going to be this 1 minus 1 divided by m to the n-kth power. Okay, and then we can approximate this by saying that this expression over here is approximately this exponential function over here. Okay, this is going to make our calculations a bit easier. Okay, so therefore the probability that any position, so the probability that a position stays 0 is going to be about this function over here. And so the probability that a position becomes 1 after you insert n keys is just going to be 1 minus that probability. Okay, it's going to be about this. Okay, so now, we have m, so this is the probability that any position I is going to be 1 after you insert n keys, right? And in this array, you have m different positions. Okay, so because each one of them, each position is 1 with this probability, then in expectation, you're going to have this number of positions, which are 1s. Right? This is the expected number of positions, which are 1 after you do n key insertions. Okay. Now, the actual number of positions, which are 1s, okay, that can deviate from the expectation. Right? So the actual number of 1s is actually a random variable, right? But the expectation of that random variable is 1 minus p times m. Okay, and furthermore, the this random variable is actually very tightly centered on its expectation. Okay, so you can actually, so if you want to make this a bit more precise, you can actually show that with a high probability, the actual number of ones is no more than this value over here. Right, it's its expected value plus something which is like square root of m. Okay, so you can prove that rigorously. Okay, but we're not going to do that part. Okay, we're just so we're going to sort of make a simplifying assumption, which is not exactly correct, but we're just going to assume that the number of 1s is exactly equal to the expected value. Okay, if you want to make things more rigorous, you can use this tighter bound, but the basic argument is the same. Okay, so then, all right, so then if the expected number of 1s is this value over here, right, then that means that, so when you go check a particular location, right, it's going to be 1 with this probability, okay? And so now we're trying to bound the false positive probability, right? So you're going to get a false positive if you check for k locations, k random locations, using your k hash functions, right? And if all of them are 1s, then that can be a false positive. Right? But what is the probability that all k locations are 1s? Okay. Well, each position is 1 with probability 1 minus p. So therefore, you have that all k positions are 1 with this probability. Okay, which if you plug in this expression over here, right, then this is what you're going to end up with. Okay. So this is the expression for the false positive probability. All right, so let's take a closer look at this expression, okay? So, so you notice that this probability here, it's a function of k, n, and m, okay? Now, what we're going to do is you're going to fix n and m, okay? So you're going to decide that you want a hash table of a certain size, so that's m. And you're also going to decide that you're going to put some number of items into the hash table. So that's n. Okay, so once you fix n and m, right, then the rest of this probability is just depends on the number of hash functions that you use. Depends on k. Okay. And so what happens is that you can actually choose an optimal k, which minimizes your false positive probability. Okay. So the basic idea is that I'll just give you the intuition first. So if you use a very small k, right? So let's say you use k equals 1. Okay, so that means that each item just hashes to one location. Then there's actually a pretty good probability that if you take two different items, they're going to collide with each other, in which case you get a false positive. Okay. So you don't want to use a very small k. But if you use a very large k, that's also bad. Okay, so for example, if you use a very large k, then even just to insert one item, you're going to hash that item to basically all of your table locations. Right? If you set k very large, you're going to hash a single item to many, many table locations. So even one item can like fill up your hash table. Right? But if you fill that table, then the next time you check for another item, right, there's a very high probability that all of these locations for the second item are already ones, in which case you can get a false positive. Okay, so that means that you don't want to use a very large k either. Okay, so there's actually some sort of intermediate k, which is like which gives you the minimum false positive probability. And to find the optimal k, all you need to do is if you fix n and m, right, then this entire thing just becomes a function of a single variable k. Oops, sorry about that. Yeah, of a single variable k. And so to find the optimal k, you can just differentiate the function with respect to k, right, in order to find the optimal k. Okay. And it turns out that the optimal k is always equal to this value. Okay, it's m divided by n times log 2. And if you plug that k into the into this expression over here, you're going to see that the false positive probability is going to be this function like that. Okay, which in turn is equal to this. Okay. So this means that now if you look at this if you look at this top part over here, okay, this m divided by n, okay, so this m divided by n is actually the number of bits that you're using per item, right? Because m is your table size, right, and each location in the table is just a single bit, and n is how many items you're storing, okay? And so this means that the more bits you use, right, the larger m divided by n, then the lower your false positive probability. Okay. In fact, the probability decreases exponentially as a function of the number of bits that you use. Okay. So as an example of this, so here we plotted the false positive probability on the y-axis and the number of bits, okay, per entry, which is this m divided by n. And so what you can see is that if you use about 10 bits per entry, okay, then you get about a 1% false positive probability, right? And then if you use, let's say, 15 bits per item, right, then you get something like a 1 in 1,000 false positive probability. Okay, so you get to choose how many bits you want to use per item, and that's going to determine your optimal false positive probability. Okay, any questions about this? Okay, so I'll just say a few more things about Bloom filters. Okay, so the first thing is that right now our Bloom filter cannot handle delete operations. Okay, and the reason that we can't do deletes is because so for example, suppose you have a Bloom filter like this, right? So we have a bunch of these array locations, right? And suppose you inserted a key, let's say x1 here, and it goes to, let's say, these two locations. Oops. Right? And then, what is this? And then let's say you have an x2, oops, which goes to, let's say, these two locations. Okay? So then what happens is that we're going to set all of these three locations to be ones. Now, one simple way that you can try to delete so suppose you want to delete x1. Okay, then one simple thing you can try to do is you can just set all of the x1 locations to be zeros. Okay, so basically you can set this location to be a 0, right? And you can set that to be a 0. Okay, so then when you do this, then you do delete x1. Right? But the problem is that you've also deleted x2 if you do this. Because now if you go check for x2, right, then x2 is going to hash to these locations. It's going to hash over here and also hash over here. And you see that the left position is actually 0 now. Okay. So now the Bloom filter is going to think that x2 is not in the set either. Okay. So that means that by deleting x1, you also deleted possibly some other items if you do things this naive way. Okay, yeah, so this simple type of delete is not going to work. Okay. However, there is a way to modify these Bloom filters so that they can support some sort of delete operations. So what we're going to do is instead of having simply bits at each of these array locations, we're going to have, so the bits can either be 0 or 1. Okay. So instead, we're going to make each array location hold a value from, let's say, 0 to s for some value s. Okay. And now each time you insert an item in there into an array location, you're going to increment the value at that array location. Okay, so for example, when you insert x1, you're going to set these things, so initially they're all zeros, right? And now you're going to set them to be ones. Okay, and after that, if you insert x2, right, then you're going to increment these locations. So this one is going to go from 0 to 1, but this value over here is going to go from 1 to 2. Okay. All right, now after you do this, now suppose you want to delete x1 now. Okay, so if you want to delete x1, then what you're going to do is you're going to hash x1 to all its locations, and then you're going to decrement the values there. Okay, so then this 1 is going to go back to a 0, and then this 2 is going to become a 1. Okay, and now if you do this, then when you go check for x2, you can see that x2 is still in the set, right? Because in order to check for x2, you're just going to check that all k locations it hashes to are larger than 0. Okay, if they're larger than 0, then you say that x2 is in the set. Okay. So now, by incrementing these positions, we've made it so that you can actually you can delete items. Okay, but there are two problems with this this method. Okay, so the first problem is that now we're going to have to use more memory for each array location, because previously you just had a 0, 1 value in the array location. So that's a single bit. Right? But now you need to keep a count of how many items hash to that location. Right? And you need to put a limit on this count, okay? Because if you allow the count to be arbitrarily large, then you need to use an arbitrary amount of memory for each array location. And we don't want to do that, right? Because the whole point of using a Bloom filter is to minimize how much storage you need for the table. Okay? So maybe, for example, you might use 4 bits per array location. Okay, so that's going to let you keep track of a value from 0 to 15. Okay, but that means that if there are more than 15 items which collide at a location, right? So each time you get a collision at a location, you're going to increment the value, and because your maximum value at each location is at most 15, then if you get more than 15 collisions at a location, then you're going to get a wraparound, right? The 15 is going to become a 0 now. And now that's going to make your Bloom filter be incorrect. Okay, so what I'm saying is that by using this new method, you can support delete operations, but now you need to control how many items can hash to a location. Because if you get too many collisions, then once again you're going to have some incorrect results for your Bloom filter. Okay, so this is not a perfect solution to the to the deletion problem. Okay, now another, oh, sorry, I forgot, I should have shown you all this animation. Yeah. Right, now the final thing I'll say about Bloom filters is that there's a kind of a nice trick that you can do with these Bloom filters, which is that suppose you have, so a Bloom filter is used to keep track of a set. And now suppose you have 2 Bloom filters, right? One for set S1 and another one for set S2. And suppose now you want to create a new Bloom filter either for the set S1 intersect S2, right, or for S1 union S2. Okay, so suppose you want to create these 2 new Bloom filters. Okay, you already have the Bloom filters for S1 and S2, and now you want to create these 2 new ones. So there's actually a very simple way to do this. Okay, so for example, if you want to create a Bloom filter for S1 union S2, okay, then all you need to do is, so this S1's Bloom filter, this is a bit array, right? And likewise, S2 here is represented by a bit array. So all you need to do is you can just take these bit arrays and OR them together. Okay, and that is going to be equal to the Bloom filter for S1 union S2. Okay, so you can think about that, and you're going to see that this works correctly. Okay, so in order to create the Bloom filter for S1 union S2, you just OR together these two Bloom filters, which is a very fast operation. Okay, right, and if you want to do S1 intersect S2, okay, then you can do S1, you can do the Bloom filter for S1 and for S2, and you can AND them together. Okay, and that is going to produce something which is, so that's not going to produce exactly the Bloom filter for S1 intersect S2. Okay, if you AND them together, you're going to get something which is approximately like the Bloom filter for S1 intersect S2. Okay, if you OR them together, you're going to get exactly the Bloom filter for S1 union S2. But if you AND them together, you get something which is like approximately like S1 intersect S2. Okay, so I'm not going to go into more details about like you know, how accurate that approximation is. But you know, these are kind of like tricks that you can do with Bloom filters. Okay, are there any questions about these Bloom filters? All right, so then in that case, I'm going to start a final topic, which is, so now we're going to see how to use randomization when we want to do string matching, or well, string equality first. Okay, so this is also called fingerprinting. Okay, so the setup for this problem is that suppose you have two people, let's call them Alice and Bob. Okay, and suppose they both have copies of a database. Okay, so we're going to represent the database as simply a bit string. So so Alice and Bob both have a bit string. Okay. And now all they want to do is they want to check whether their bit strings are equal to each other. Okay, in other words, whether their databases are consistent with each other. Okay, yeah, so now, so if Alice and Bob are distributed from each other, okay, then in order to check whether their databases are exactly equal to each other, they would have to send this bit string for the database to each other. Okay, and that's a very expensive operation, right? Because it involves some sort of communication between two remote locations, and that's going to be very slow. Okay. So instead, we want to have a way that Alice and Bob can check whether their two strings are equal to each other and use much less communication. Okay, so what we're going to do is instead of sending the entire bit string, the entire database to each other, instead they're going to calculate a small value which is called a fingerprint of the database, and then they're going to send that small fingerprint to each other. Okay, so that's going to be a lot less communication than sending the entire database. And the fingerprints have this property, which is that so Alice is going to compute a fingerprint from her database, and Bob is going to compute a fingerprint from his database. And if these two fingerprints are different, then the databases are definitely different. Okay. On the other hand, if the fingerprints are the same, okay, then probably the databases are the same. But there's a small false positive probability. Okay, there's a probability that they're actually different, even though we say, even though the fingerprints are the same. Okay, so then what you get from using this fingerprint overall is that you know, you're going to dramatically reduce how much data you need to send. Okay, so I'll just tell you the you know, how much it is. So if your database has size n, right, then if you send the entire database, that is going to take n bits. But these fingerprints are actually only log n bits large. Okay, so you can go from sending a linear amount of data to a logarithmic amount of data, right? So that's a huge reduction. Okay, and also there's a small. However, what you lose is that you have the small false positive probability, where the fingerprints are the same, right? But the databases are actually different. Okay, but we're going to bound that probability. We're going to show that this is not too large. Okay, so yeah, so I'm probably not going to finish all of this today, but let's see how far we get. Okay. All right. So the way that we're going to do this fingerprinting is that we're going to think of Alice and Bob as so they have these databases which are these bit sequences. Okay. So suppose Alice has n bits and Bob has n bits. And now we're going to treat these bits, these bit sequences as simply n-bit integers. Okay, so you're just going to read this a1 up to an as an n-bit integer. Okay, or more concretely, you can do this computation, which produces an integer, an n-bit integer. Okay, and likewise for b. Okay, right, and now the fingerprint for a and b is just that we're going to choose a prime number. Okay, so I'll tell you later how you choose that prime number. And then you're going to compute f of a, which is going to be, so the fingerprint for a is just going to be a modulo this prime number. Okay, right, guys, sorry, there's a lot of noise in the background, so I'm going to just hold on 1 second. Okay, so I'm going to, stop this noise. Okay, yeah, sorry about that. Okay, so as I was saying, the fingerprint for a is just going to be a modulo the prime number. Okay, and likewise the fingerprint for b is just going to be b modulo the prime number. Okay, so now what we're going to do is Alice is just going to transfer f of a to b to Bob. Okay, and then Bob is just going to check that this f of a is equal to his fingerprint f of b. Okay, and if that's true, then Bob is going to think that Alice has the same database. Okay, and if f of a is not equal to f of b, then Bob is going to say that Alice has a different database. Okay, so that's the entire algorithm. Okay, you just compute a modulo p, you send that to Bob, and then Bob compares that value to b modulo p. Okay, and now how much data do you need to transfer? Okay, well the fingerprint, because you're computing a modulo p, then this is a value less than p. So therefore you only need to transfer, and to represent a value less than p, you just need log p bits. Okay, so therefore you only need to transfer log p bits from Alice to Bob instead of n bits, right? If you want to check for whether, if you send the entire database, you're going to send all n bits. And here we're just going to send log p bits. Okay, and then later on, we're going to see that p is actually polynomial in n. So therefore, log p is basically linear in log n. Okay, so we're going to see that in the end, you only send a log n number, order log n bits from a to b. All right, so let's prove that this algorithm actually works correctly. Okay, so the first thing is that we don't have any false negatives. Okay, meaning that if the algorithm says a and b are different, then a and b are definitely different. Okay, and the reason for that is, so the algorithm is going to say a and b are different if f of a is not equal to f of b. Okay, but if f of a is not equal to f of b, then definitely a does not equal b. Because if a equals b, right, then f of a, which is a modulo p, is equal to b modulo p, which is f of b. Okay, so if these two fingerprints are different, then the two values, a and b, must be different. However, there can be false positives. Okay, meaning that so the algorithm is going to say that a and b are the same if f of a equals f of b. Right? And that's going to happen when a modulo p equals b modulo p. Okay? And so if a mod p equals b mod p, right, then either a actually equals b. Okay, so that's a true positive, right? Or a is not equal to b, but p divides a minus b. Okay, if p divides a minus b, then a modulo p is going to be equal to b modulo p. Okay, and in that case, you're going to get a false positive. Okay, so we there's no way to avoid the second possibility. Okay, where a and b are not equal, but p divides a minus b. However, you can bound the probability that it occurs. Okay, and the way that we're going to do that is we're just going to pick a random p. Okay, and the idea is that if A does not equal B, okay, then if you pick a random P, then it's unlikely that your random prime number is going to divide A minus B. Okay, and if P does not divide A minus B, then you won't have any false positives. Okay, so it's quite likely, so if P doesn't divide A minus B, then you're going to see that f of A is not equal to f of B, and that allows you to detect that A and B are different. Okay, and and so the bigger that you pick P, okay, the lower you can make the false positive probability. Okay. However, if you pick a very large P, right, then because you have to transfer log P bits, you don't want to pick a very large P. Okay, so you want to pick a P which is still small, but it can also decrease your false positive probability. Okay, so so I think our class is actually supposed to end at this point. Okay, so then what I'll do is next time we'll continue with this analysis. So we'll analyze the false positive probability, and we'll see how large we need to make P to make this probability not be too large.